Okay, good morning everyone. So we're finally getting into transformations today, and I know we've talked a little bit about it, and the fact that you've all taken Pre-Calc 11 means you have worked with transformations before, but now we're going to formally start talking about translating graphs and expanding and compressing and reflecting graphs. Today we'll look at translating. So in math, translating means shifting a graph to the left and to the right, up and down. The shape of the basic graph stays the same, but we're just moving its position to the left and right and up and down. And as we've talked about before, you can always create a table of values to find points to plot on the graph, but it's a lot easier if we can just recognize what is the underlying shape, what are the transformations, and then apply the transformations to the basic function. So I know we're all very familiar with our basic quadratic function y equals x squared. I'm going to use that as an example. Okay, so let's call this our basic function y equals f of x. Okay, if I were to rewrite the equation like this, y is equal to x minus 2 all squared plus 3. Okay, the shape of those two functions are identical to one another, but they just have a different placement on the graph. And so what we might remember is that this function here has been shifted or translated 2 units to the right and 3 units up. Okay, so there's our example. Here's what we're doing. If we're comparing some function y equals f of x to this, and I call this the skeleton transformed equation. Basically what's happening is our p-value here is going to shift the graph to the left and to the right. So we'll just make a note of that. This is shifting the graph left and right. And our q value is shifting the graph up and down. Okay. So if p is positive, so I'm going to say if p is greater than 0, then we shift the graph to the right. If p is negative, then we shift the graph to the left. Okay, similarly, if q is positive, we're shifting the graph up. If q is negative, we're shifting the graph down. Now, I just want you to be aware of one thing here. So I'm going to jot down this skeleton transformed equation. So we've got f of x minus p plus q. Okay, so let's say that p is 2. Okay, what does the equation look like? Well, we would get f of x minus, and we're plugging 2 in for p. So we get f of x minus 2 plus q. Okay, so that x minus 2 inside the brackets is translating the function 2 to the right. Okay, but what happens if p is, for example, negative 1? Okay, what does the equation look like? We get f of x. So this is x minus p, and if p is negative 1, we've got x minus negative 1, which is x plus 1, and then plus q. Okay, so we've got x minus 2 in brackets. This is shifting 2 to the right. We have x plus 1 in brackets. That's shifting 1 to the left. Okay. Now the other form you might see this looks like that. So we've got y minus q is equal to f of x minus p. And all that's happened here is we've looked at the isolated version of the equation. So if we isolate y, we get y is equal to f of x minus p Bringing that negative q across to the other side, it becomes positive. Okay, but those two things are equivalent to one another. Okay, so let's look at some examples here. We want to describe what change happens to the graph of the function y equals f of x based on different changes to x and different changes to y. Okay, so the first one, we're going to change x, or we're going to replace x with x minus 2. So the equation looks like this. Y is equal to f of, and we're replacing or changing x with x minus 2. And now we want to identify what the transformation or what the translation is. And we know that we've got a shift of 2 units to the right. Okay. So again, this is our base function here, y equals f of x. What happens to it when we make these different replacements? Okay, the next one, we're going to change y to y plus 5. So we've got y plus 5 is equal to f of x. Now we can isolate y. We don't have to, but we can. I think we're more comfortable seeing equations where we've isolated y. We would get f of x minus 5 on the right-hand side of the equation. That's a q value of negative 5. Our translation is 5 units down. Okay. Next one, we're going to change x to x plus 6, and we're going to change y to y minus 7. Okay. Other terminology we will hear is we are replacing y with y minus 7. We are replacing x with x plus 6. So here's the equation. Replace y with y minus 7. Replace x with x plus 6. Okay, again, I'm going to isolate y. We get y is equal to f of x plus 6 plus 7. And let's just identify what our p-value and what our q-value is. Okay, so careful particularly with the p-value. Think about whether p here is positive 6 or negative 6. And to think about it, think about what we're plugging into this skeleton equation here. So because we have x plus 6 in the brackets, that means our p-value is negative 6. Okay, x minus negative 6 gives us the x plus 6 in the brackets. Okay, and our q value is positive 7. What are the translations? We've got a translation of 6 units to the left and 7 units up. Okay. Let's do the opposite. So this time we're given the translations and we need to build the equation. Okay, so what's the equation look like if we're translating 1 to the left and 8 down? Okay. If we're translating 1 unit to the left, we are replacing x with, we are replacing x with x plus 1. Okay, if we're translating 8 units down, okay, we have to be careful with this one. We are replacing y with y plus 8. Okay, so let's input those into our equation, and then we can look to isolate y and just see exactly what that looks like. Okay, so our basic function is this: y is equal to f of x, and we're gonna replace that. So the first one, we'll replace the y with y plus 8. And we'll replace the x with x plus 1. And if we were to isolate y, we get y is equal to f of x plus 1 minus 8. Okay, so that's a translation of 1 unit to the left and 8 units down. I'll put a box around both of these as they're both our final answer. Okay, next one. We're translating 3 units to the right and 1 unit up. Okay, so translating 3 units to the right, we are replacing x with x minus 3. And translating 1 unit up, we are replacing y with y minus 1. Okay, so plugging these things in, we get y minus 1 is equal to f of x minus 3. And isolating y, we get y is equal to f of x minus 3 plus 1. Okay, so we've got a translation of 1 unit up and 3 units to the right. And again, I'll put a box around both of these. Okay, and moving on. Okay, so we're going to graph the following by hand. Now again, we could create a table of values, but that's going to be time consuming. What I want to do is recognize what is the base underlying function. So the first one is our basic parabola y equals x squared. So here's our basic parabola. Oops. Okay. Now let's identify the translations and then apply them to that graph. Okay, so we've replaced x with x minus 3. This is a shift of 3 units to the right. We've replaced y with y plus 4. Our q value is negative 4. That's a shift of 4 units down. Okay, so I'm going to take the vertex of our basic function and I'm going to go 1, 2, 3 to the right, 1, 2, 3, 4 units down, and I will redraw our basic parabola. Okay, so the two shapes should be identical to one another, but the one in red has been translated 3 units to the right and 4 units down. Okay, next one. Again, we could create a table of values, but what I want us to do is identify that the basic underlying function here is y is equal to the square root of x. Okay, and we want to get to the place where we can draw these basic functions without creating a table of values. Okay, so the square root of x, our basic radical function, is the top half of a sideways parabola. Okay, so there's our base function there. And we'll identify the translations. So we've replaced x with x plus 5, so this is a shift of 5 units to the left. And we have a q value of 2. This is a shift of 2 units up. Okay, so I'll take the vertex there. I'm going to go 1, 2, 3, 4, 5 to the left, and 1 and 2 up. And then we'll regraph. I've just added one more point there that was not on the graph of the basic function. Okay, but the shape stays the same. We've just translated it. Okay, next one, at the heart of this is our basic absolute value function. Okay, here's what our absolute value function looks like. Connect the dots. Okay. Now, I will rewrite the equation having isolated y. So we're going to get y is equal to the absolute value of x minus 4 and plus 6. And let's identify the translations now. So we've got a shift of 4 units to the right and 6 units up. So again, I'm going to take the vertex and we'll go 1, 2, 3, 4 to the right, 1, 2, 3, 4, 5, 6 units up, and we'll redraw that graph. So we should get something like that. Okay, and the last graph here that we'll look at, our underlying function is our basic reciprocal function. Okay, so y is equal to 1 over x. If I draw that, it looks something like this. Okay, maybe not the best drawing, but you get the idea. Now, invisible to us, but something that does exist in our basic reciprocal function is we have both a horizontal asymptote and a vertical asymptote. I'm going to draw these in, and then I'll talk about them really quickly. Okay, so we've got a horizontal asymptote along the x-axis, and we have a vertical asymptote along the y-axis. Okay, so for the purposes of what we're doing here, I'm going to explain the asymptotes as being these invisible barriers that the graph of the function is going to get infinitely close to. Okay, so as the graphs get bigger and bigger and bigger and smaller and smaller and smaller and closer to 0, okay, along the y-axis, the graph, which is in blue, is going to get really close to those asymptotes, but it's never going to touch them and it's not going to cross them. Okay, now later on in the course when we look at graphing different functions, we're going to flip our understanding of asymptotes on their head, and we'll see where we actually can cross asymptotes with the graph of a function. Okay, so from here, let's identify now what the translations are of this transformed function. And I'll just start by rewriting the equation having isolated y. So we get y is equal to 1 over x plus 2, and then minus 5. Okay, so essentially we've replaced x with x plus 2. This is going to shift the graph 2 units to the left. We've replaced y with y plus 5, which gives us a q value of -5, which shifts the graph 5 units down. Now with this reciprocal function in particular, the easiest way for us to draw the translated version is to shift those asymptotes. So I'm going to take the vertical asymptote and I'm going to shift it 2 units to the left. So I'm just going to go 1, 2 to the left, and I'm going to redraw that vertical asymptote right here. Okay, so the next thing we will do is we're going to shift or translate that horizontal asymptote 5 units down. So I'm going down 1, 2, 3, 4, 5, and we'll draw that in again. Okay, and then redraw our basic reciprocal function. So it's going to look something like that, and something like that. All right. Moving along. Okay, so we are given this point here. It's got an x coordinate of 2, a y coordinate of 4, and it's on the graph of some function y equals f of x. Okay, now if we look at two other functions that incorporate some translations, where does that point that had coordinates 2 and 4, where does it move to on the transformed function? Okay, so here's what I'm going to do. I'm just going to jot down what the translations are to begin. Okay, so f of x minus 3, we have a translation of 3 units to the right. Minus 5, we have a translation of 5 units down. Okay, so we'll do this. We will start. Here's our starting point. X coordinate of 2, y coordinate of 4. Okay, so if we're translating 3 units to the right, we are adding 3 to the x coordinate. Okay, so that takes us to 5 and 4. And if we're shifting or translating 5 units down, we are subtracting 5 units from the y coordinate. And so we end up with 5 and -1, and that's our final for the first question. Okay, next one, the translated function is f of x plus 6 plus 3. So we've got a shift of 6 units to the left and 3 units up. Translating 6 units to the left, I'm going to subtract 6 from the x coordinate. 2 minus 6, we get -4. 3 units up, we're going to add 3 to the y coordinate. 4 plus 3, we get 7. And there's our final answer. Okay, and the last page here. So here's what we are told. We're told that the function f of x is graphed below, and we want to graph each translation. Okay, so here's what I'm going to do to begin. I'm just highlighting, we call these vertices. So I'm highlighting each of the vertices, and I'm going to apply the translations to each of the vertices and then connect the dots as I go through that. Okay, so the first one is f of x plus 3. So here we've got a shift of 3 units to the left. So 1, 2, 3 to the left. 1, 2, 3 to the left. So I'm going to connect those 2 dots. Up here we've got 1, 2, 3 to the left. We'll connect these. Next one, 1, 2, 3 to the left. One, 2, 3 to the left. And 1, 2, 3 to the left. There we go. And I'll label this, so our graph in blue is the graph of f of x plus 3. Okay. The next one, we will do this in red. We've got f of x minus 2, so this is a shift of 2 units down. Okay, we're going back to our initial function f of x. I'm going to highlight each of the vertices of f of x, and so we're translating each of those vertices 2 units down. So we're going down 2, connect the dots, down 2, connect the dots, down 2, connect the dots, okay, and there we go. So I'll label this in red. This is the function f of x minus 2. Okay, and so the last one here, let's choose another color. We'll go with green. So this is f of x minus 1 plus 2. It's a translation of 1 unit to the right and 2 units up. So I'm going to highlight the vertices of f of x again, and then we'll translate each of those vertices. So 1 to the right and 2 up. 1 to the right and 2 up. We'll connect those dots. 1 to the right and 2 up. 1 to the right and 2 up. 1 to the right and 2 up. And there we go. And we'll label this. This is the function f of x minus 1 plus 2. Okay. And the last one here, so given the function y is equal to 1 over x, determine the equation when translated 3 units to the right and 2 units down. Okay, so we can think about this in terms of replacements. So if we're translating 3 units to the right, then really we're replacing x with x minus 3. Okay, this one's a bit harder to visualize. If we're translating 2 units down, we're replacing y with y plus 2. Okay, it's only after we isolate y that we see the q value that intuitively makes sense. Okay, so we'll build this up. I'm going to replace y with y plus 2. And I'm going to replace x with x minus 3. Okay, so that works right there. There is our basic reciprocal function translated 3 units to the right and 2 units down. But I'll also rewrite it having isolated y. So we would get y is equal to 1 over x minus 3 and minus 2. Okay. And the very last one, so we're given this equation and we want to come up with the equation that shows a translation of 2 units to the left and 5 units up. Okay, so if we're translating 2 units to the left, then we are replacing x with x plus 2. And if we're translating 5 units up, then we're replacing y with y minus 5. Okay, so we'll build this up. Y becomes y minus 5. And this is equal to, now we've got x cubed. We're going to replace that x with an x plus 2. I'm going to do so in brackets. Okay, so this is what we're working on right here, that x. We've replaced it with x plus 2. We still need to cube that. Now we're adding 2 times x squared. So we've got plus 2. And again, I'm going to replace x with x plus 2 in brackets. We're squaring it. Now minus 5 times x. We're replacing that x again with x plus 2. And then finally we are adding 3. And that's it.